Alright, welcome to the Chapter 4 homework review, Chapter 4 homework 1. The scores this week were pretty good. We averaged about 10 out of 12, which is a pretty usual average for us, and pretty good considering it was an exam week, and I'm sure many of you had your focuses elsewhere. So on this homework assignment, we covered some of the important topics in Chapter 4, a lot of things about molecular structure, VSEPR, hybridization, and a little bit on molecular orbital theory. So the topics, though, that we had the most trouble with seem to be molecular polarity, so that's what we want to spend most of this review going over, and then a couple other things as well. So one thing that I did get a lot of questions about, and I want to clear up before I go into problems, is how do we classify molecular shapes? And we have these two different classifications, electron group arrangement versus molecular shape, which we can also call molecular shape, geometry, structure, a few different ways of naming it. So if we ask you for the electron group arrangement, that's going to be the arrangement of all of the electron groups, which includes bonding and non-bonding or lone pair electrons. So for the electron group arrangement, it's going to be all of them considered, and it's going to be one of 5 possibilities: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And all of these correlates to a specific number of electron groups, or a specific steric number, as I called it in class. Linear would be 2 electron groups, trigonal planar 3, tetrahedral 4, trigonal bipyramidal 5, and octahedral 6 electron groups. So that's going to be the arrangement of all the electron groups, but then for molecular shape, or molecular geometry, if we call it that, or molecular structure as it's sometimes referred to, we consider only the atoms and not the lone pairs. And this has a lot more possibilities. So within each of these 5 electron group arrangements, there are multiple geometries that are possible, and that's going to be determined by how many lone pairs you have. So keep in mind that we do have 2 ways of classifying the shapes of molecules, and we might ask you really about both of those, and I'll try to point out those differences as we go through some of these questions. Now, in general, we did pretty well with the questions dealing with VSEPR and molecular shape, but I do want to go over one that we had a little bit of trouble with, and it's the molecular structure of xenon pentafluoride cation, XeF5+. So anytime we're doing problems in this chapter, anything with VSEPR, anything with hybridization, we have to start with a good Lewis structure. So we'll review that quickly for this one. So xenon is one of our noble gases over here, so it's going to have 8 valence electrons. And then we have fluorides, we have 5 of them. Fluorine is in group 7, 7A over here, so it's going to have 7 valence electrons. And then we have our positive charge. Remember that that's going to remove 1 electron. So anytime we have a positive charge, we have fewer electrons. So this is going to give us a total of 42 electrons. So there's really no shortcut here. We have to draw the Lewis structure, because in order to give the molecular structure, we need to know not only how many atoms are bonded to the central atom, but also how many lone pairs there are. So when we draw this out for xenon pentafluoride cation, we start with 5 single bonds to our fluorides. We complete their octets with lone pairs. So that's going to be 5 octets, that's 40 of our electrons, so we still have 2 more that need to go on the central atom. Alright, so many of us, I think, that missed this problem forgot about the lone pair in the central atom. So when we write this out in AXE notation, this is going to be AX5E, 5 atoms and 1 lone pair. This means we have 6 total electron groups, so it's going to be an octahedral electron group arrangement. But then this asks for the molecular structure. So when we write out the full structure, everything's going to be arranged in octahedron, because there's 6 electron groups. But one of those is a lone pair. The rest are going to be atoms. Doesn't matter where we put the lone pair. They're all equivalent here. And this is what we call square pyramidal. Alright, so many of us forgot about the lone pair, and choice A here was the second most popular answer because many of you just assumed, oh, there's 5 things at the central atom, it's got to be trigonal bipyramidal, but that lone pair counts. That lone pair occupies one of the positions on an octahedron, but when we talk about the molecular structure, we're just talking about the structure of the atom. So you have a square of fluorines, and then you have one apical fluorine, which is our square-based pyramid. That's why we call it that. Okay, so don't try to take any shortcuts on these. You have to know not only the number of atoms that are bonded to the central atom, but also the number of lone pairs. We did have difficulty with one of these problems dealing with hybridization. Again, in general, we did pretty well with the hybridization questions, but here we want to know, we have this organic molecule here, and we want to know the hybridization of the nitrogen atom. So again, for hybridization, we also need to consider lone pairs. And as I've mentioned before, when we're doing these sort of organic structures that are mostly, carbon, hydrogen, nitrogen, a little bit, oxygen, things like that, we can put the lone pairs in pretty easily because all the atoms should have a complete octet except for hydrogen, of course, which only has 2 electrons. So this oxygen should get two more lone pairs to make its complete octet. And the nitrogen, which has 3 bonds right now, 6 electrons, should get 1 more pair of electrons. And then if we want to draw the lone pairs on chlorine also, they're going to go in there to complete its octet. So really we want to, especially for the nitrogen atom, which is what we're interested in, we want to know both the bond atoms and lone pairs. So if we zoom in on this nitrogen here, if we want to write it in AXE notation, the nitrogen has 1 atom bonded to it, the carbon, and it has 1 lone pair. So this is sort of an AXE structure. That means the steric number, or the total number of electron groups, is 2. And so if we write out the hybridization for this, remember we're going to hybridize on nitrogen just the s and the p orbitals. There are no available d orbitals. We have 2 electron groups, so we need to do sp hybridization. So that's going to be the correct answer for A. So basically you have 1 sp orbital forming your sigma bond with carbon, 1 sp orbital holds the lone pair. You're going to have sp hybridization for this nitrogen. Alright, so for any time you're trying to find hybridization, you need to figure out what are the number of electron groups that are attached to that atom. This nitrogen has 2 electron groups on it. That corresponds directly to sp hybridization. Alright, the rest of the problems here deal with molecular polarity, which is one of the more difficult topics in this section to wrap our head around. So I'm going to do 3 problems here that deal with molecular polarity. So the first one dealt with dichloroethylene, CH2Cl2, which has 3 different forms or isomers shown in the following figures. These are kind of small, so I'll reproduce them. Alright, so one of the structures, the first one, looks like this. And the question we're asking is, I guess I didn't write the question here, how many of these are polar, or it may have been worded as how many of these have a non-zero dipole moment. I'm not sure what the exact wording was in this. I forgot to reproduce the second half of the question. Anyway, we have these 3 isomers, and the question asks us which ones are polar, basically. Okay? So this is the first one, second one. Sorry, the second one should be... I'm ahead of myself here. So I have an H, Cl, Cl, H. And then the last one has the hydrogens over here, chlorines over here. Okay. So we have 3 structures, and we want to know which ones are polar. And so remember, we have to consider for molecular polarity, we have to consider the individual dipole moments for each of the bonds, and then we have to decide whether they cancel out, which would give us a nonpolar molecule, or whether they don't cancel out, in which case then there is net molecular polarity. So CH bonds are pretty close to nonpolar, but they do have a little bit of a polarity towards carbon. So if we draw the individual bond dipoles for this one, there's going to be small bond dipoles pointing towards each carbon, and then the carbon-chlorine bonds are also polar and sort of in the same direction. So clearly these bond dipoles don't cancel each other out, they actually reinforce each other, and so we have a net dipole moment in this molecule that's sort of going to point down towards the chlorines. So this one's going to be polar. If we look at our second structure here, we have a bond dipole going from hydrogen to carbon, a bond dipole going from hydrogen to carbon, And then we have dipoles going from carbon to chlorine. And in this case, these all cancel out. So I'll draw red X's through these. So this dipole here and this dipole here are equal and opposite, so they cancel out. And then this dipole here and this dipole here are equal and opposite, they completely cancel each other out. Alright, so this is a case where the individual bond dipoles are completely opposite of each other, so they cancel out, and this one's going to be nonpolar. And then finally, if we look at the last structure here, we have two bond dipoles pointing towards carbon, two pointing from carbon to chlorine. Remember that these bond dipoles point towards the more electronegative atom. I guess I should have mentioned that at the outset. So these individual dipoles sort of point from left to right. They don't cancel each other out, they reinforce again. And so this has a net left to right dipole in the orientation that I've drawn it. So this one is also polar. Alright, so 1 and 3 are polar. This is structure 1, this is 2, this is 3 as they were labeled in the problem. And so 1 and 3 are going to be the polar molecules, or the ones that have a non-zero dipole moment. Alright, so again, when we're drawing these out, we have to really think about the three-dimensional structures. These are all flat molecules here because the carbons are sp2 hybridized. So that means they're completely planar. And so all of these bond dipoles are in the same plane, and the ones that are then going to be completely opposite of each other, pointing towards each other, are the ones that cancel out. So these two, one points, in this direction, this one points opposite, this one we point from towards the top right, this one points towards the bottom left, and we have a net cancellation. Alright, so that's sort of the idea here. This was a little bit more of a complicated one because it's a slightly more complex geometry. We don't just have one central atom here, but again, think about the individual dipoles and whether they cancel out. Alright. So the last two are a little bit more straightforward because they deal with sort of our AX, AXN type structures, the more typical Lewis structures that we've been drawing. And again, we were looking here, we have PF5, BRF3, BRF5, SF4, which does not have a molecular dipole moment, or alternatively we can say which one is nonpolar. And again, this is going to be a situation where we have all of the bond dipoles canceling out. We're looking for the case where all the bond dipoles cancel out. So for PF5, I'm not going to go through the Lewis structures in great detail, but you would get an AX5 structure. There's no lone pairs on the central atom, which gives us a trigonal bipyramidal geometry. And so in this case, all the bond dipoles cancel out and is nonpolar. And even if that's not obvious from the picture, so these three on the trigonal plane cancel each other out, and then you have the two apical positions, one pointing up, one pointing down, those dipoles cancel out. Fluorine is more electronegative than all of these, so it's always, the bond dipoles are always going to point towards fluorine, but this one's going to be nonpolar. And all of the AXN structures where there's no lone pairs, so this is AX5 with no lone pairs, those will all give nonpolar molecules as long as all the X's are the same. So we don't have to think about this one. BRF3 though, when we draw the Lewis structure for this, we get AX3E2, which is T-shaped. So drawing it more accurately, we get sort of this geometry with the lone pairs on the central atom. And in this case, the bond dipoles don't cancel out. So these two more or less do. They're opposite of each other, but we have a net dipole moment pointing towards this fluorine on the right here, so this one's going to be polar. And then I skipped one, but that's BRF3, which is polar. This one's nonpolar, so we think that's our answer, but let's verify the rest. BRF5 is going to be, if we draw it out, AX5E. We saw this structure earlier. And then so BRF5 is going to be this square-based pyramid structure. And again, the bond dipoles that are on the square base more or less cancel each other out. But we have one dipole pointing towards this fluorine, so we have a net dipole pointing top to bottom. Alright, so this one's going to be polar as well. And any of the structures with one lone pair are going to be polar, so we don't have to also think hard about that one. And then finally SF4, this one's going to be AX4E, so again we have to consider the lone pairs as well. And so SF4 is going to be this seesaw geometry. Alright, there we go. Alright, so SF4 has a seesaw geometry. Again, two of them sort of cancel each other out, but then we have a net dipole pointing towards these two, and a net dipole pointing left to right. So this is going to be polar. And again, any structure that has one lone pair on the central atom is going to be polar without even thinking about it. Alright, so the last three are polar, so choice A is clearly the winner, the only one that's non-polar. So I gave you a table in the notes when we talked about molecular polarity, which lists all of the AXE notations and whether they're polar or non-polar. One way to approach these problems is just to memorize that whole table, but again, drawing the structures and really thinking about the individual bond dipoles can be helpful as well. But all the structures that have one lone pair are going to be polar, so that's an easy one to remember. All the structures that have zero lone pairs are going to be non-polar. Again, that's only in the situation where all of the X's, all the outer atoms are the same. Alright, so a very similar question here. Which one has sp3d hybridization and no dipole moment? Again, we're looking for the non-polar one. So for this, there's sort of two parts to the problem, so it depends on whether you're more confident in your ability to predict hybridization or more confident in your ability to predict the molecular polarity. I do think in this case, in this homework assignment, we showed that we're pretty good at doing hybridization, so for many of you, that's probably the place to start. So let's find out which of these are the correct hybridization first, and then we can try to figure out if they're the right polarity. So some of these are sort of repeats from what we saw before. So PCl3 we haven't seen yet, but that's going to be AX3E, which gives us sp3 hybridization. There are 4 electron groups, so it's going to be sp3. BF3 is going to be AX3 with no lone pairs, so this is sp2 hybridization, only 3 electron groups. SF4 we just saw above, that's AX4E, 5 electron groups, so it's going to be sp3d. So this one has the correct hybridization. BRF3 is AX3E2. We saw one above that was very similar, or exactly the same. So BRF3 we saw was AX3E2, also 5 electron groups, also sp3d hybridization. And then finally PCl5. Up above we saw PF5. PCl5 has the exact same structure, AX5, also sp3d hybridization. So choices C, D, and E all have the correct hybridization, and then the question is, of these three, which one is nonpolar? And one of them has to be, because there's obviously a correct answer for this question. So SF4 we saw above, for any of the ones that have one lone pair, they're going to be polar. So SF4 again is seesaw. And these two bond dipoles more or less cancel out. They're not perfectly linear, but they're pretty close. And then we have net dipoles pointing from the left to right. So this one's polar, and it has that one lone pair again, anytime it has one lone pair. BRF3, a little bit less obvious, but again, if we draw the structure out, it's pretty clear. This is one of those T-shaped structures. Now we have 2 lone pairs on the trigonal plane. Again, pretty much a cancellation in the apical directions, but we have a net dipole pointing towards that fluorine. So this one's going to be polar as well. And then as we saw above, PCl5, which is the same structure as PF5, it's AX5, no lone pairs. And so anytime you have no lone pairs, the bond dipoles cancel out. And this is going to be nonpolar. Alright, all of the individual bond dipoles, there are still a net polarity towards chlorine, but they all cancel each other out. And this structure is a little bit complicated, so it's not the most obvious why they cancel out, but the 3 vectors that are in the plane of the trigonal plane are all canceling out, and then you have the 2 apical positions that cancel out as well. Alright, so PCl5 is also nonpolar and sp3d, so this is the only one that has the correct hybridization and is nonpolar. If we want to care about the polarity of these other two, this one's going to be polar, AX3E. It has 1 lone pair, so it's definitely polar. This one, AX3, no lone pair, so it's definitely nonpolar, but it's not the correct hybridization, which is why choice E is the only one that works out. Alright, that takes us to the end of the homework review. In summary, make sure you review polarity. That's the molecular polarity. That was the part that seemed to be the most difficult for us on many of these. And again, for these AXE structures, there's each AXE notation has a polarity associated with it, either polar or nonpolar. So become familiar with those and really try to understand how the three-dimensional shapes relate to the polarity. And the rest of the questions we did pretty well on overall. All right, that takes us to the end, so I will see you next time with the next homework assignment.